Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The landscape of late 19th century mathematics presented a profound and tantalizing challenge. The geometric intuition cultivated over centuries, rooted in the visualizable spaces of Euclid, was training against the new frontiers of higher dimensions. Following the conceptual breakthroughs of Bernhard Riemann, mathematicians could speak of manifolds, abstract spaces of arbitrary dimension possessing local Euclidean properties. Riemann himself, in his study of complex analysis on what we now call Riemann surfaces, had introduced the idea of connectivity numbers to describe the topology of these two-dimensional objects. His student, Enrico Betti, attempted to extend these notions into higher dimensions, offering an early glimpse into the internal structure of these esoteric forms. Yet their work, while foundational, was incomplete. It provided powerful intuitions about connectivity, about the number of cuts a surface could endure before separating, but it lacked a systematic, rigorous, and computable language. The core problem remained unsolved: how to classify n-dimensional manifolds based on their intrinsic, qualitative properties, completely independent of their particular embedding or geometric shape. Into this intellectual void stepped Henri Poincaré. In 1895, he published his seminal paper, Analysis Situs, a title translating to the analysis of position. With this work, he inaugurated a new field of mathematics, what we today call algebraic topology. His expressed goal was ambitious and clear. He sought to create a science of pure situation, a qualitative geometry that would distill the essence of shape down to its fundamental connective properties. To achieve this, he moved away from the differential geometric methods of his predecessors and invented a powerful combinatorial and algebraic machinery. This new approach would transform the intuitive idea of shape into a set of calculable algebraic invariants. The first pillar of his revolutionary framework was the concept of homology. Poincaré began by proposing that any continuous manifold could be decomposed into a finite collection of simple building blocks, which he termed polyèdres, the precursor to the modern simplicial complex. This involved subdividing the space into vertices, edges, triangles, tetrahedra, and their higher dimensional analogues. With this discrete representation established, he could translate the geometric problem into the language of linear algebra. He defined a series of incidence matrices that captured the precise relationships between cells of adjacent dimensions. For instance, one matrix would encode which edges bound which vertices, and another would encode which faces were bounded by which edges. From the properties of these matrices, Poincaré extracted a sequence of numbers, which he called the Betti numbers in honor of his predecessor. The kth Betti number, denoted P sub k, was defined through the rank of these incidence matrices. It measured the number of independent k-dimensional cycles, or closed chains, that were themselves boundaries of a k plus one-dimensional chain. For instance, P sub 1 represents the count of independent, non-contractible one-dimensional loops. In essence, the Betti numbers provided a discrete, algebraic signature for the number of k-dimensional holes in a manifold. To make this abstract machinery concrete, consider the familiar surface of a torus, the shape of a donut. After triangulating its surface into a polyèdre, Poincaré's method yields a precise topological signature. The zeros Betti number, P sub 0, equals 1, signifying the torus is a single, connected component. The first Betti number, P sub 1, equals 2. This corresponds to the two fundamental and independent loops on the torus surface, one circling the hole longitudinally and the other circling it latitudinally. Neither of these loops can be continuously shrunk to a single point while remaining on the surface. Finally, the second Betti number, P sub 2, equals 1, capturing the single two-dimensional void enclosed by the surface itself. This set of invariants, 1, 2, 1, provides an unambiguous characterization of the torus connectivity. Any continuous deformation of the torus, any stretching or bending, leads this algebraic signature unchanged. Poincaré's inquiry extended beyond this static counting of holes. He introduced a second, dynamic method for probing the structure of a space, a concept that would later blossom into the fundamental group. He analyzed paths, specifically closed loops, which he called lacets, that begin and end at the same point on the manifold. He then considered their continuous deformations, asking which loops could be smoothly transformed into one another. If a loop could be continuously contracted to its starting point, it was considered trivial. The existence of non-trivial loops revealed essential features of the space's connectivity. This method of classifying equivalence classes of loops under deformation, or homotopy, provided a more detailed picture of topological structure than Betti numbers alone. It laid the conceptual foundation for one of the most powerful and central objects in modern topology. In developing these tools, Poincaré was explicitly building upon the legacy of his forerunners. His Betti numbers were a direct, rigorous, and computational generalization of Riemann's intuitive connectivity numbers for surfaces. He also acknowledged Enrico Betti's prior efforts in higher dimensions. However, Betti's definitions were tied to the properties of potential functions on the manifold and lacked the coordinate-free, combinatorial universality that Poincaré achieved with his polyèdre and incidence matrices. Poincaré's work supplied the missing formal language, a robust framework capable of transforming the nascent study of position into a mature and powerful branch of mathematics. This initial paper, for all its brilliance, contained subtle errors and profound claims that would fuel mathematical research for decades, beginning a new epoch in our understanding of space itself. Within the grand intellectual architecture of analysis Situs, two monumental claims form the central pillars, supporting the entire edifice. These assertions, one concerning the fundamental nature of his new numerical invariants and the other revealing a deep, hidden symmetry within geometric forms, were both breathtaking in their ambition and, initially, imperfect in their execution. The paper presented a stunning blueprint for a new mathematics, yet the full rigor would emerge from the very process of defending and refining its foundational ideas. It is in the examination of these core theorems, their initial proofs, their latent flaws, and their ultimate vindication, that we witness the dynamic process of mathematical creation at its most The first of these pillars was the assertion that the Betti numbers were true topological invariants. This proclaimed that the numbers calculated from the incidence matrices of a given polyhedral decomposition were intrinsic properties of the underlying manifold itself, change the triangulation, subdivide its faces, and the numbers would remain constant. This was a radical departure from prior geometric measures that depended on specific coordinate systems or embeddings. Poincaré's proof strategy was based on the idea of a common refinement. He argued that for any two different triangulations of a manifold, one could find a third, finer triangulation that was a subdivision of both. He then demonstrated, using his algebraic formalism, that the Betti numbers were stable under such subdivision. The reasoning was elegant and powerfully intuitive. However, its foundation contained a subtle fissure. The existence of a common refinement for any two triangulations, while geometrically plausible, was a substantial theorem in its own right, one that Poincaré assumed without a formal proof. His argument relied upon a geometric intuition that, while correct, lacked the axiomatic certainty demanded by the new standards of rigor he himself was helping to establish. The claim was sound, but the proof was incomplete. This very gap became a generative force in the field. It was almost 2 decades later that James W. Alexander, building directly on the program Poincaré had initiated, provided a completely rigorous demonstration of the topological invariants of homology. The episode illustrates a recurring theme in the legacy of analysis Situs. Its brilliant insights, even when incompletely proven, served as powerful signposts, directing the course of mathematical exploration for future generations. The second monumental claim was the Poincaré Duality Theorem, a statement of profound and unexpected symmetry. For a closed, orientable manifold of dimension n, the theorem asserts a remarkable relationship: the kth Betti number equals the n minus kth Betti number. In more intuitive terms, for a 3-dimensional space, the number of independent 1-dimensional tunnels is identical to the number of independent 2-dimensional enclosed voids. The theorem connects features of different dimensions in a beautiful, reciprocal dance. Poincaré's initial proof in the 1895 paper, rooted in his calculus of incidence numbers, was complex and ultimately unsatisfying even to him. He sensed a deeper, more geometric truth underlying the algebraic result, a truth his first attempt had failed to fully capture. He delivered the definitive argument in a later supplement, and it remains a masterpiece of conceptual clarity. The key was the construction of a dual polyhedral decomposition. For any triangulation of the n-manifold, Poincaré constructed a second, dual triangulation. The vertices of this dual structure correspond to the n-dimensional cells of the original. The edges of the dual correspond to the n-1-dimensional cells of the original, and so on. A k-dimensional cell in the primal triangulation is uniquely intersected by an n-k-dimensional cell in the dual. This geometric pairing, a form of exquisite orthogonality, provided the mechanism for the proof. The incidence matrix for the chains of a certain dimension in the original triangulation revealed itself to be, up to a change of sign, the transpose of the incidence matrix for the corresponding chains in a dual triangulation. This direct algebraic correspondence, born from a purely geometric construction, immediately established the equality of the Betti numbers. The proof was a triumph, replacing a difficult calculation with an illuminating structural insight. The evolution of analysis Situs was also driven by external critique. In 1898, the Danish mathematician Poincaré constructed an ingenious counterexample to one of Poincaré's subsidiary claims. He devised a three-dimensional manifold with the same Betti numbers as the three-dimensional sphere, yet which was fundamentally different. This demonstrated that the Betti numbers alone were insufficient to fully characterize the topology of a space. Poincaré's response was a model of intellectual integrity. In a subsequent supplement, he acknowledged Poincaré's discovery and used it as a springboard for a deeper investigation. He returned to his algebraic machinery and found that it contained more information than he had first extracted. He discovered that the homology of a manifold possessed a finer structure, which he termed torsion coefficients. These integers captured the way certain cycles could fail to be boundaries, while a multiple of that cycle would form a boundary. This led to a more powerful set of invariants, a richer description of shape that could distinguish Poincaré's space from a sphere. The Betti numbers measured the number of independent holes, the torsion coefficients measured their twisting. This correction, prompted by a colleague's challenge, transformed his theory and laid the groundwork for the modern algebraic formulation of homology groups, with their distinct free and torsion components. The immediate aftermath of analysis Situs validated its revolutionary character through the very challenges it invited. The paper's initial formulation of homology, while powerful, contained ambiguities that became fertile ground for the next generation. Its direct influence is powerfully demonstrated in the work of the Dutch mathematician L.E.J. Brouwer. While Brouwer's methods were often intensely geometric and intuitive, his celebrated fixed-point theorem and his proof of the invariance of dimension were profound responses to the foundational program Poincaré had launched. Brouwer was establishing the rigidity of Euclidean space, proving that its topological properties were intrinsic and unchangeable. He was, in essence, providing rigorous answers to the types of fundamental questions about spatial characterization that Poincaré's paper had made it possible to ask. The dialogue between Poincaré's algebraic machinery and Brouwer's geometric intuition defined the field's early trajectory. The most transformative legacy of the paper, however, grew from its imperfections. The computational complexity of Poincaré's incidence matrices and the subtle error corrected by Poincaré revealed a need for more profound structural understanding. This necessity catalyzed the 20th century's great algebraic turn in topology, a movement spearheaded by the unparalleled abstract vision of Émile Noether. Xu and others recognized that Poincaré's Betti numbers and torsion coefficients were shadows of a deeper algebraic object. They reconceptualized the entire framework. The chains, cycles, and boundaries were no longer mere geometric lists but elements of algebraic groups. The boundary calculation became a formal map, an operator. The result was the modern theory of homology groups. This reformulation was an act of profound distillation. The nth homology group of a space is understood today as a quotient group, the group of n-dimensional cycles, which is the kernel of the nth boundary operator, divided by the group of n-dimensional boundaries, which is the image of the n plus first boundary operator. This definition, born from Noether's axiomatic approach, transformed a cumbersome computational tool into a powerful, elegant, and functorial invariant. The language of topology had changed forever, shifting from matrices and numerical counts to the sophisticated discourse of exact sequences and algebraic structures. Perhaps no single element of the paper's legacy looms larger than a question Poincaré posed in a 1904 supplement. Having successfully classified all closed two-dimensional surfaces, he turned to the next dimension and asked if a similar characterization was possible. He speculated that any closed three-dimensional manifold in which every loop can be shrunk to a point must be topologically equivalent to a three-dimensional sphere. This became the celebrated Poincaré Conjecture, a problem so simple to state and so difficult to solve that it would guide a century of mathematical progress. Its resolution was a saga in itself, culminating in the work of Grigori Perelman in the early 2000s. Perelman's proof was a testament to the interconnectedness of modern mathematics, a reality Poincaré himself embodied. To solve this purely topological problem, Perelman employed deep analytical tools from differential geometry, specifically Richard Hamilton's program of Ricci-Flow. This partial differential equation, which smooths out the curvature of a manifold over time, provided the mechanism to deform an arbitrary three-manifold into a canonical shape, confirming Poincaré's century-old intuition. The solution required a synthesis of fields, demonstrating that the questions raised by analysis Situs were so deep they could only be answered by the combined power of topology, geometry, and analysis. The conceptual toolkit, introduced in 1895, has since migrated into domains far beyond the imagination of its creator. The fundamental idea of characterizing shape through connectivity and holes now powers topological data analysis, or TDA. In this field, practitioners analyze massive, high-dimensional datasets by treating them as point clouds in a geometric space. By computing the persistent homology of these clouds, They can identify robust topological features, clusters, and voids that are invisible to traditional statistical methods. This approach finds structure in the seemingly chaotic data of neuroscience, genetics, and materials science. Similarly, the algebraic structures born from analysis Situs are now fundamental to theoretical physics. Concepts like topological insulators, materials whose exotic electronic properties are protected by their underlying topology, are described using invariants directly descended from Poincaré's work in topological quantum field theory. The algebraic formalism of homology and its descendants provides the framework for calculating physical observables in a way that is independent of the manifold's local geometry, a profound echo of the original quest for geometric invariants. The ultimate significance of analysis Situs, therefore, is found in its generative power. It was a work of towering genius, yet its true force came from its incompleteness. It was less a final, polished monument and more of a grand, ambitious blueprint, replete with tantalizing open questions and challenging theoretical gaps. It did far more than solve problems, it created a new universe of them. The paper threw down the gauntlet, compelling a century of mathematicians to invent entirely new languages and build more powerful tools to explore the world it had revealed. In its brilliant, flawed, and visionary pages, we see the very engine of mathematical progress. A singular work defines a field, its questions become the research programs of generations, and in answering them, mathematics transforms itself into something richer and more powerful than before.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.